All right, let's get started. Hi, Trevor. I don't think Setsu is in the room. I don't believe, but hi, Setsu. All right, let's get started. So we have a few slides from last time we got to clean up, and then we'll get on with it. So authentication, just an overview of what authentication is, and mostly how we store passwords. Is we're going to get a username and password from the user. That's their registration. We're going to, this is just authentication. We're going to get a username and password from the user. We're all familiar with that side, just being users of the internet. Generate a random salt, which should have a bit of, I haven't used that word yet, which is going to have a bit of randomness to it. These salts should be pretty long. They can be, as long as you want them to be, but they should be pretty long. I know that's a super vague statement, but we'll talk about it. Actually, we might not. I better do it right now. The salt does not add any extra randomness. I guess I did use this word last time, right? I can start saying entropy. It doesn't add any entropy to the password. So no matter how long your salt is, it doesn't gain any security. The password does not get any stronger because of that. So a salt isn't just a answer to everything. You just add a big random salt to your password and QED security. Not the case. But these do limit the effectiveness, actually destroys the effectiveness of rainbow tables. And also when an attacker compromises a database full of hashed passwords, since they're all salted, they can only attack one password at a time because they need to know the salt for that specific hash to be able to attack that hash. So before, what I mentioned briefly last time, they attack a database, they have all these hashes, they take a guess, and they take the hash of that guess and look up, does this hash match any of these passwords? They can't do that anymore. They have to pick one specific user to attack at a time, and then attack that specific user with their specific salt. So the salt limits certain types of attacks, does not add any objective, security, does not add any entropy to our crypto systems. And good thing I backed up. I didn't even mention this slide. For all our encryption needs, or encryption, we're not even encrypting yet. For all of our hashing needs, for all of our password needs, bcrypt library. Love it. Love this library. The bcrypt library, it's already in the requirements.txt of the handout code. That's my way of saying, yes, this is allowed. You can use this on your homework. I never went into the, as a general rule, I don't think I even said this yet this semester. As a general rule, if I don't go into the details, the nitty-gritty details of something in lecture, then you can use a library for it. I didn't go into the nitty-gritty details of how to compute a hash, how to generate a salt, things like that. So you can use libraries for those things. And the bcrypt library is like the go-to library for hashing passwords. This is the library that, hesitant to say everybody, but this is the library that they use out in industry, out in the world. Your hashes sitting in databases probably is the bcrypt library. It's probably hashed with bcrypt. Bcrypt exists in just about every language. I'll hedge my bets a little bit there, but there's a bcrypt library for any language I've used, including Python, of course. So use bcrypt. It'll do all of your password hashing needs in 2 lines. 2 lines. 1 line to hash the password and generate the salt. It's 3 method calls, but 2 of those are in 1 line to generate your hash and your salt. And then what bcrypt generates will contain the hash and the salt in a single value. So you don't even have to worry about storing the salt separately. Bcrypt will take care of the details there. And then 1 line, when you get a password and you need to authenticate it, ask bcrypt, hey, this hash and salt that I got out of my database, does it match this plain text password? And it'll extract the salt, append the salt, hash the password, and check the hashes. It'll do all that for you. 2 lines of code. That's all you need for all of your password needs. Just don't forget to add those 2 lines of code. It's probably the hardest part, just remembering. Yep.
Just to clarify, when you say random, I'm assuming you mean more pseudo-random, not actually.
Yeah, we don't have any literal randomness. So yeah, pseudo-random. And you can use libraries for that too, generating your random tokens. If you want to pull in a library for that, I believe Python just has a built-in library that'll generate tokens for you. Also, since I'm on this topic, JSON, I never went into the details of the format. Same with URL encoding. I didn't go into the detail. I did a little bit, I guess, with that format, but decoding, percent encoding, what a pain in the butt. If you want to use libraries for those, for URL encoding specifically, we're just not going to test with any reserved characters. It'll always be strictly ASCII and non-reserved characters, so we won't test with percent encoding. But if you do want to support that and pull in a library to do that, that's fine. Import JSON, json.loads, json.dumps, go for it. Knock yourself out with those ones. Because I didn't say, JSON, you have these open braces, closed brace, that defines an object. This is how you escape quotes. I didn't do any of that, so I don't expect you to. So that's a good rule of thumb for the, even for the homework. For the project, of course, you can use any library you want. But for the homework even, if I don't go into the details, use a library. If I do go over the details, you're using a library for that. Obviously, I went into the detail of HTTP request and response. I expect you to code all that. So that's your rule of thumb of how to answer the question of what's allowed or not. And if you're ever in doubt, just ask. I'll let you know in probably a second for most things. Okay, so registration, we get a username and password. We invoke bcrypt. We say bcrypt, hash this password with a random salt, and then store that in your database. I'll use SHA-256 for my examples. I don't believe bcrypt uses, I feel silly even saying that. Bcrypt uses its own algorithm. It's not using SHA-256, but I'll use SHA-256 in my examples and demos coming up. And then store that stuff in your database. Username, salt, and hash. With bcrypt, salt and hash are a single value. So you're only storing 2 values in your database. The salt and hash are all in one big thing encoded in a way that bcrypt knows how to read. Authentication, we get a username and password again. We do get a plain text password. For what it's worth, we get plain text passwords on our server, and we handle plain text passwords. Never, ever store plain text passwords. But in memory, we do handle plain text passwords. That's why very briefly on Monday I said somebody who can inject code into the server can still recover passwords. That's because they could inject code that during the login process takes that plain text password and stores it somewhere as plain text somewhere that they can view it. So we take the plain text username and password, get the salt and hash out of the database, mash that with our password in bcrypt, or what bcrypt is doing is taking the salt, appending it to the password, taking the hash of that and comparing it with the hash that's stored. And if the hashes match, then the user is authenticated. If the hashes do not match, they're not authenticated. It's a quick binary, do they match or not? And if you're even one character off in the password, the hashes will look extremely different. They'll look absolutely different, which is the feature we want from our hash functions. So nobody even gets the information that they were close to your password because the hashes are completely different. And redirects, kind of a one-off topic, but I didn't feel like putting it in homework 1 content because we don't need it to homework 2. But in your login form, if they're oh man, I'm blanking. I'm pretty sure, I'm like 90% sure, what I put in the document, if they successfully log in, you should redirect them back to the home page. And if they don't log in, I forget. But somewhere in the homework doc anyway, I'm not 100% where. One of the login or register, you need to respond with a 301 redirect or any 300 level redirect to redirect the user back to the home page, because the page is going to reload when that form is submitted. Those are HTML forms, which are going to reload the page. So if you want to respond with a redirect, you're going to give them a 300 level, a redirect. I'm using moved permanently for this example. And then add a location header, which is the path that you're going to redirect the user to. The browser is going to look at this redirect, say, OK, let me send a new request for this location, and then load that page to the user. So the user just gets redirected to the new page, and usually the user doesn't even know about it. This one drives me nuts. I don't think I even put a slide on it. This one drives me nuts, but since there's no content put a content length of 0. This is one of my big pet peeves. But put a content length of 0, or else Firefox won't respect your redirect. So to fix this in Firefox, content length of 0, the HTTP spec, the RFC says if there's no content length, you should assume a content length of 0. Firefox does not do that, at least not for redirects. So if you have no body to your response, Firefox is just going to hang if there's no content length. So add your content length of 0 just to shut Firefox up, have it stop trying to read bytes of the body, and have it immediately follow the redirect. So don't forget your content length of 0 just for Firefox, because you'll get it works in Chrome but not Firefox, and I swear I've looked for a legitimate reason for this, and I'm convinced that Firefox is in the wrong. I tried looking through Firefox source code to figure out where, but I don't know, I couldn't find it. So we're just going to add that content length of 0, even though I'm pretty sure Firefox is in the wrong here. And then the redirect is going to make another request for this path, which can be relative or absolute. So this is a relative path. If I just do /new path, that's going to send a request, a redirect, to that path using the same protocol, host, and port as the initial request. So if I requested CC 312 on 8080, and this old path gave me a redirect to /new path, same, and then new path. The path only is going to change, but you can, if you want to redirect someone to another server, or if you want to change the protocol, which is pretty common. If somebody says HTTP : / whatever, I'm going to send them a redirect to HTTPS / whatever. I'm going to redirect them to HTTPS. I want everybody using encryption out there, which is a homework 4 topic. We'll get there. But we can, if we want to change the protocol or the domain or the port, we're going to give an absolute path, which is very legal, a very valid legal thing to do. So if this path, I want to redirect them to Google for whatever reason, I can do that. If you want to do which a student has done in the past, if you want to write a URL shortener and host that, this is how you would do it. Have your URL listen for certain paths and respond with redirects to absolute paths and be able to randomly generate those shortened URLs. This is how you would do it with redirects. And I do have a slide on it. Yeah, Firefox gets really confused after that. So put your content length of 0 on your 301s and on your redirects, and Firefox will do your redirects. But if you come to office hours, it redirects in Chrome, but not Firefox. I don't know. I'll probably just say pull up these slides. Go to the last slide. Okay, so that's our cleanup from last time. Let's get into today's content. Is there any single or double new line after the redirect location? Doesn't matter. Yes, it still has to end in that blank line. Every HTTP request and response has to, absolutely must contain that blank line. Must contain that /r/n/r/n. Every single one. If it's a GET, a POST, a request, a response, does not matter. It must contain it. If there is no body, that's the last 4 bytes of the request or response, but it does have to be there. All right, authentication tokens. So let's take a look at, we kind of just overviewed authentication. I guess I don't have to do this one again. So we have registration and authentication. And with authentication, all we have is authentication right now. Somebody sends username and password. We take that username, go to our database, say, give me the record for this username. That gives me the salt and hash. I put the salt on the end of the password, hash it, and check if the hashes match. That's authentication, and that's all we can do. If the hashes match, they're good. If the hashes, let me reword that. If the hashes match, they are authenticated as that user. If the hashes do not match, they are not authenticated as that user. That's all we can do right now. That's all we've learned about. So how do we use this to let people access their private data and make authenticated posts to the server? So how do they send and retrieve data as themselves? If you make send a post request to the server that needs to be authenticated as you, how do we do that? More to the point on the homework, if somebody is logged in and they send a message to chat, we need to add their username to that request, but they're not sending their username. And even if they were, we'd have to authenticate that. We have to make sure that that is actually the person who sent that message, because we don't want people spoofing messages and submitting messages as other people, making posts as other people. We don't want that. And we don't want anybody accessing somebody's private data. So how do we authenticate these requests when they're getting and sending information to the server? Well, we have them send their username and password, right? So when you want to say anything in chat, if it's an authenticated chat that's going to have your username next to your message, you type your chat message, you type your username, you type your password, you click send. You want to reply to somebody, type your message, type your username, type your message. You want to react with an emoji, you click the emoji, you type your username, you type your password, right? That's all we can do. That's all we have is authentication. So that's all we can do. And no, please don't do this. This is not a solution. Do not ever. If you make an app like that, 0 people will use your app. Maybe immediate family members, that's about it. And they'll only use it once. All right, so we have another option. And here's a reasonable option that has some key flaws. But we know about cookies, right? Let's just jam that username and password into cookies. And now that username and password is sent on every request without the user having to type them in physically every time. The username and password are just sent along every request. This is a reasonable solution. It's not what we're going to do. Do not do this. Do not do this, because those cookies have to be stored on the user's machine, and we do not store passwords in plain text. No, not even client side. Do not store these in plain text anywhere. If a user wants to store their password in plain text somewhere, that's their decision. We're not making that choice for them. We're not making them do something that's insecure. You've working on homework 1, you know how to check your cookies now. You just go into the browser console application, there's all your cookies. If those cookies contain plain text passwords and your friend's laptop is right there, guess what? You got their password. And people who like to use the same password for multiple apps, you probably have their password to a lot of things if they're one of those people. We're not going to open up our clients to that. Not going to happen. There's a more, I didn't put on the slide, but there's a lesser reason for this too, is performance. Hashing a password using bcrypt is pretty slow. Not terribly slow, but if you're talking about millions of users and billions of requests, it can add up. Where what we're going to do is a bit faster than using bcrypt for passwords. Yeah.
I don't know if I missed this, but let's say, like, when the client initially sends the password via post request, how do you make sure that that's encrypted?
We don't yet. So the question, when the user initially sends their password, how do we ensure that's encrypted? So far, we have not done anything with encryption yet. So right now, your app for homework 2 is not going to be secure. I'll put that out there. It's not going to be secure. The problem is that username and password for registration and for login, it's floating through the air in plain text. That's bad. We're not going to solve that until we get to HTTPS. Then we're going to have that flying through the air encrypted, but we're not doing that yet. We're right at the point where we can do secure storage of the passwords. And then in homework 4 content, that's when we're going to secure them flying through the air and secure those packets. So no encryption quite yet. So the solution that we're actually going to do is authentication tokens, the name of today's lecture. We're going to use authentication tokens. So now when a user logs in, or when a user registers, they register exactly the same way as they used to. And then when they authenticate with their username and password, they're going to give their username and password just like they used to. And then when they are authenticated properly, the hashes match with the salts and all that goodness, we're going to issue an authentication token. We're going to generate a random token with a lot of entropy. We're going to store that token in our database associated with that user. So now we're going to have username, hashed salted password plus hash, all that in one with bcrypt, and their authentication token all in the database under that user's record, or however you want to manage your data in your database. I would just throw them all in one record or one document in MongoDB. And then set that token, what am I trying to point to, as a cookie for your user. So in your response, when they authenticate, set that token to a cookie. And then whenever they send another request, we're going to see that token, and we're going to say, hey, I know that token. That's the token I gave this user. I know you are that user. I missed one. Well, it's on the next slide anyway. I'll talk about it then. Or not the next slide, but. So now we're issuing a random token. This token is going to have enough entropy that nobody can guess it. And then once we see that token again, we say, I know who you are, because nobody could possibly guess this token. You must be this person that I issued this token to. Now we don't have an authentication. Well, we do still have an authentication system, but we leveled it up to a login system. Now users can actually log into our app and stay logged in. Now every request is going to have your auth token, and that's the way that we're going to verify that you are who you claim to be. Actually, you don't even have to claim to be anything. We just see that auth token and say, oh, you have this token. I gave this token to this person. You must be that person by assumption. I added the note. I might as well talk about it. These should expire at some point. It's up to you. For your homework, I don't care. They can just not expire. But out there in the world, this is something you and your team and your company have to think about and decide, when should our tokens expire? And they should expire server-side. Have some timestamp in the database that says this token expires at this time. You can set the cookie to expire, but if I think I've only said this once or twice, so probably like second or third time out of 1,000. Never trust your users. You set an expiration date on your cookie. Well, the user doesn't have to respect that expiration date. They can change that expiration date. They can do whatever they want with that cookie. It's their cookie. They can do anything they want with it. Anything on the front end, the user can manipulate, and some users will manipulate it to do malicious things. So don't just rely on client side. You can set the expiration, but don't rely on that. We set the expiration in the homework just to make sure it's not a session token, because then regular users have less functionality, but we don't rely on that expiration date for the expiration. So server-side expiration too. Most major sites these days seem to set these expiration dates as like decades in the future. There are some apps that I've logged into once and use every day and never log into again. These things usually expire almost never. But it's something your team would have to think about in the real world. It's not something I'm going to worry about in 3.12, but in the real world, your team has to sit down and say, when do we want our tokens to expire, if ever? Like for banking apps, these things seem to expire in like 10 minutes. I'm in the middle of doing something, it's like, you're logged out. Or the hub kicks me out constantly, expires my tokens, all of us. And these tokens should be quite random. We need a lot of entropy on these things, because these tokens need to not be able to be guessed by attackers. If an attacker can guess a token, they can effectively be whoever they guess, whatever token they guess. So if an attacker sets their token to some random value, sends a request, what your server is going to do is take that token, look it up in your database and say, have I issued this token to anyone? And if you have, then pull that username and say, this is this person. So if your auth tokens are not high entropy, they're just going to send a bunch of random requests with a bunch of random tokens until one of them says, I know who you are, you're this person. So if you don't have a lot of entropy here, and say you have 1 billion possible tokens, 1 billion entropy, so like 20 bits of entropy, and you have 1 million users, 1 million authenticated logged in user sessions, it's only going to take roughly 1,000 guesses for an attacker to get one of those accounts. If they're not concerned about who they attack, they're in 1,000 guesses, they're going to get one of those accounts, and they are that person. Because your server takes that token, it's not looking at anything else. It just says, I issued this token to this person, you are that person. Your server's not going back to username, username, yes, but password, hashes, salts, none of that's involved at all. It's just, does this token match a token that I issued? If yes, we're good. So make sure you have a lot of entropy on these. I forgot to put it on the homework document, so technically you don't have to on the homework. But for real world, my goodness, these need to have a lot of entropy. 2 to the 80 is still the standard. More is always better, especially when this is just one variable in your code. Why not make it higher than 80 and just make sure you got even more security? And I said this a bunch of times, but this is the key. I think I meant to delete this slide, but this is the key bullet here that I was hanging on to. I didn't delete it. The possession of that token does verify that the user authenticated in the past. HTTP is stateless still. We cannot have any persistent connections. We're just doing this to simulate a persistent connection. So if they have that token as a cookie, we say, yeah, you authenticated. Doesn't matter if they did or didn't. We're not double checking that. We're not going back through our logs or anything. We're just saying, you have this token, you are that person. Yep. Yep. Yes, it's similar. So the big thing we're avoiding, because somebody can grab this token, the big thing we're avoiding, one of the big things we're avoiding is if a user uses the same password in multiple apps, this stealing this token isn't going to compromise their other apps where they use that token, because these tokens are going to be very different, but the password would be the same if the user is sloppy with that. Another reason, it just kind of freaks the user out. If you see a plain text, like if you look through your cookies of an app and you saw your plain text password as a cookie, you might run away from that app. So we don't want to freak our users out too, even though these things are very vulnerable. But also, tokens can be easily revoked. Changing a password, asking a user to change their password, it's kind of a big deal. Asking them to change their token, you can do that in the background without them even noticing. So they're easy to update. You can update them on every request if you want. So a lot of advantages. But it is a good question because it is very vulnerable still. And speaking of vulnerable, they are very vulnerable. These tokens are, I think I even say in this slide, even though it contradicts what I just said, they're about as sensitive as passwords. If you have one of these tokens, but for the reasons I just said, they're not quite as vulnerable as passwords, but they're pretty dang close. If you have somebody's token, you effectively are that person according to that server. So these are very vulnerable, which means if we have a database of these tokens, that database is a lucrative target just like a database of unhashed passwords. Not quite that bad, but it's almost as bad as having a database filled with unhashed plain text passwords. So we do not store these tokens in plain text either. We do not store raw tokens. We're going to only store hashes of these tokens. So we'll store hashes. So if somebody does compromise the database, they get a bunch of hash tokens and they have no chance of reading those tokens. There's a lot of nuances in there in that statement, but they have no chance of recovering these tokens. With passwords, I mentioned this and that. There's a whole bunch of issues with that. With tokens, we don't have the same issues we have with passwords because we control the entropy of these tokens. We generate a token with 200 bits of entropy. Nobody's cracking that token. They're not doing it. We store a hash of that token. Nobody's breaking that. We can't guarantee that our users are going to give us passwords with 200 bits of entropy. In fact, they won't. Most users won't give us anywhere close to that entropy. But these tokens, we can guarantee they'll have enough entropy. If we don't feel good about the amount of entropy, we change one variable and bump it up. Super easy. And we're storing hashes of those, so they can't use those attacks that they use to attack our password hashes. They can't use the same attacks, including the rainbow tables. They can't use rainbow tables because the entropy is so high. The rainbow table would have to be ridiculously huge, more storage space than exists on Earth. They would need to even come remotely close to even still not even being able to touch these hashes. So salt not needed. In fact, you shouldn't salt these because it makes your database lookups more complicated. If you don't believe me, try salting them. You'll see you have to write a lot of extra code to do your database lookups. So just hash them. That way you can hash the token you get and then look up in your database, give me the record where the hash token is this. If you salt, you can't do that lookup. I said try it and see how hard it is, but I gave away the answer anyway. So you can salt if you're paranoid, but it really doesn't gain anything. Those rainbow tables don't exist that can crack a hash of a high entropy value. Don't exist. They can't exist. Mathematically, they can't exist. And then when we get a request, we check that cookie. Does it contain the token? If it does, I kind of just walked through this one, but if it does, we look up the username associated with that token, and that request is from that user. According to our server, that request came from that user, period. That's how our server is going to do it. Now, it might not have actually, it might be a compromised token, but our server will treat that request as coming from that user. If the token is invalid or the cookie isn't set or the user's trying to do something that they're not trying to do, we're going to respond with one of these 400 level errors. We're going to say, hey, client, you're doing something wrong. That's our 400 level errors. Either a 401 if the user isn't logged in at all. If they're not logged in, they're unauthorized. They can't access anything that's protected if they're requesting a protected resource. For our homework, this would be deleting a chat message. If they're not logged in, it would be a 401. I didn't put that in the testing procedure. The testing procedure doesn't say have an unauthenticated user try to delete a post. So the homework says 403 forbidden. This is if a user is logged in, but they're trying to do something that they shouldn't be able to do, that they're not allowed to do. So that's the 403. In the testing procedure, it's 2 logged in users, one of them trying to delete the other one's message. It's a 403 forbidden, but unauthorized, if you see a 401, it just means you're not logged in at all. So you can't do that. Maybe you're allowed to do it, maybe you're not, but you're not logged in, so we can't tell. And then protect all your features. Don't just... never trust your users. Don't just trust that your front end is going to do the job of security. Always always do these checks server side. These checks have to be server side. Don't just say, well, I didn't put a link to that user's profile. I didn't give that link to that person, so they shouldn't have that link, so I don't have to authenticate requests for that link. No, that's not security. That's not security at all. If you get a request for that link, for that path, you need to authenticate that request server side. Has to happen server side. Never ever trust your users. Don't trust your front end. Users can change 100% of your front end. They have full control over your front end. Do not trust them. And when I say this, I'll clarify now as good a time as any. When I say never trust your users, we like to think our users, they're our customers. They're not going to try to break stuff, which hopefully generally true. But it's not just our users who have access to our site. If our web apps, if our web app is available on the web, on the internet, guess who has access to it, who we want to have access to it is everybody, anybody who wants to use it, which might include people who are not intending to be users of our site for its intended purpose. These are usually going to be attackers masquerading as users. That's when we say never trust your users, because we don't know who our user is. We can't get a request and say, oh, this request is from that guy. That guy's an attacker. We can't do that. So just don't trust any request from any user for any reason. Always verify everything server-side. Because cookies, I guess we're not protected against this anyway, but cookies can be stolen. So our authentication tokens are very valuable. If somebody steals that token, which is a pretty lucrative target for attackers, if you want to log in as your friend and they won't give you their password, don't do this, by the way. But you can get their laptop, go to cookies, get their auth token, grab that token, So somebody can steal these cookies. And when we talk about, I think I'll put it in the cross-site request forgery lecture next week, how to steal these cookies, in the HTML injection is where I want to put it. If somebody can steal these cookies and they're stealing auth tokens, it's bad news. So let's get to the demos. Okay, let's get rid of this. Let's get rid of this. And I just want to show a few things. So first I'm going to use some bcrypt. This is in your requirements.txt, so it should be installed, and then I'm going to import bcrypt, as long as you're running pip and doing that stuff. And this, I will give this one away too. I was going to say bcrypt, just read the docs, which I am going to have you read the docs for something, but I wanted to do this demo, so I added a little bit here. But bcrypt has hash password, which takes a byte string, or a byte array of bytes. I'm using a byte string here, and a salt, which is optional, but I'm using bcrypt.gensalt. It'll just generate your salt for you. And this does take an optional argument. I believe it defaults to 10. 12. Defaults to 12 of how many rounds of the salt, which is partially how large that salt is going to be. I thought it was the size of the salt, actually. But number of rounds, I don't know, maybe it's correlated to the size. I don't know, I'm not looking it up right now. But we're going to generate the salt and hash the password. And when this runs, what we'll get is a value that looks like this. If you see values that look like this in your code, in your print statements, in your database, this is what is expected. This is the output of bcrypt's hash algorithm. It's going to give you something like this. It's going to start with some meta information about the what's being stored, about the salt and the hash. I can see just by guessing here that the 20 is going to be the salt. So we're starting with, this is what the salt parameters are. And then the salt, the first thing, I'm just printing out a salt with 20 rounds. So here's my salt. In my hash, I get a salt with 20 rounds, and then somewhere the salt stops and the hash starts. So I get one single value that has my salt and my hash encoded in a way that bcrypt can read it. And then bcrypt is expecting something in this format when you check a password, which I'll leave you to read the documentation. It's one of the easier libraries for the documentation because this is the main use case. So right on their home page, it's like, here's how you do that. So I'll leave it to you to get that documentation. And then I'm using SHA-256 for my example. You don't have to use SHA-256 for yours, but if you want to SHA-256 hash your tokens and store them instead of using bcrypt, it is slightly recommended for a reason I briefly mentioned earlier, that SHA-256 is faster than hash password. Not really our concern in lecture, but if you get in the habit of that and carry that with you, you can get some efficiency later on down the road. But I'm going to use the SHA-256 hash to hash a value. I'm just going to hash pass, my beautiful secure password, and then print the hex digest of it, which is going to give me this. Here's a SHA-256 hash of the string PASS. Actually, we can, no, I'll do this for the example, but I will need a 5-letter word. I used to ask for a 4-letter word, but I get bad words when I ask for that. But I need a 5-letter word. If somebody can get that in chat, I'll pick whatever is my favorite if there's multiples. But I'm going to go to the internet. 256 calculator. I'm going to use this one. This is the one I linked from the slides from Monday for what it's worth. It's the first one that comes up. And I'm going to hash pass. I'm going to grab this hash. I'm going to go to PyCharm. I'm going to paste this hash. And what we'll see is that it's identical. SHA-256 is SHA-256. It doesn't matter if it's a Python implementation or what I used online, which is almost certainly a JavaScript implementation, unless it's going to the server side and then the server's hashing and then returning. But SHA-256 is always going to return the same thing no matter where the algorithm's implemented. The algorithm is the algorithm regardless of its implementation. So I'm getting the same exact hash for that input no matter where I go. So just to prove that that is doing what it's supposed to be doing, and if I go back here, let's grab a word, drone, Jackie, maybe, Scala, Jesse. Jesse's got 3 votes. I don't know if I like that one. I'll go with Jackie. I'll do the capital J too. No, I'm going to do a lowercase j actually. Okay, so I'm going to compute this hash. This hash has not touched my code at all. My code has no clue that that is going to be the hash. I'm going to paste my hash here. I'm using lowercase letters only. That's why I didn't do the capital J. And I'm going to call this inconspicuous method called brute force. I'm going to run this thing. All I did was paste the hash into my code. My code has no idea what the plain text was, and it computes the plain text as Jackie. So as the name implies, this is a brute force attack. It increases the length by 1 each time and keeps checking every combination using this alphabet until it finds a hash that matches what we put in. And even if, just to drive this point home, I generated a salt up here. So I'm going to grab this salt right here. I'm going to paste it right here. So I'm going to tell my algorithm, hey, I have this salt that was just randomly generated. Very long salt, lots of entropy. I'm going to paste that to the end of my plain text password here. Grab the hash. And how long do you think it'll take my algorithm now? If that. Same. The hash does not add entropy. It does not prevent any attacks other than attacks like rainbow tables. It's not preventing my brute force attack, which is admittedly pretty dumb. It's just checking everything. It's not preventing the dictionary attacks, which are more scary, the ones that are going to start with the common passwords and go through common words in the dictionary. Not going to prevent against those. So I have just the lowercase letters, upper and lowercase that I don't want to use. Then full alphabet, which is going to be special characters, numbers, and everything. If we use the full alphabet, I'm not going to change the hash and salt, but my algorithm is going to have to do a lot more checks. It's going to be a bit slower. We're still going to get there, but maybe not before the end of the lecture. Even at length 4, we're taking a while. It's going to take a bit. We'll let that run and head over here and take a look at this setup that I have. So let's talk about entropy. How long is my algorithm going to take to crack a hash using brute force? Well, our first example, we had an alphabet of size 26. I have a password length of 5, and I'm going to estimate how many attempts per second my machine can guess. And just kind of feeling out the numbers, how long it took. My algorithm's getting about 100,000 guesses per second. It's a pretty sloppy algorithm, admittedly. It can be optimized. I didn't optimize it. And even my dumb algorithm is 100,000 guesses, 100,000. 100,000 guesses per second. So let's run this and get some information. What I want to print out is the total entropy, the bits of entropy, which is log base 2 of the total number of guesses that are required. And this is alphabet size raised to password length. That's going to be my total entropy. And then log base 2 of that is bits of entropy. And then how many seconds, minutes, hours, days, years it's going to take to crack that password. So let's run this. And with an alphabet size of 26 and a password length of 5, a completely random string generated using that alphabet of length 5 is going to be 11,800 million, that many. About 11.9 million possible strings that we can make. So at worst case, that many guesses, which is 23.5 bits of entropy, and it's going to take my computer about 2 minutes to crack that. Now I switch that to the other alphabet. We can kind of calculate how long it's going to take that one to run. Roughly, it can stop once it gets to lowercase j, so it's a little off. It's not absolutely worst case, but it's about 90 characters, uppercase, lowercase, numbers, special characters. And we might not, looks like we're not finishing that at this lecture. 16 hours. We get up to 32 bits of entropy, still not secure by any means. But it's taken my crappy little algorithm half a day, a little over half a day to compute. 2/3 of a day to compute. Okay, that's fine and good, but an attacker isn't going to limit themselves to 100,000 attacks per second, attempts per second. So let's crank this up to like an upper bound of what we think an attacker is capable of. So let's say this is a very sophisticated attacker, a really great coder, who also has control over a botnet and has thousands, maybe even millions of machines trying to crack your password, just your password. So let's see, 1 million, 1 billion, 1 trillion, a quadrillion. Let's say a quadrillion. They can get a quadrillion guesses per second, which isn't, it's a lot, but it's not completely outside the realm of possibilities. Today, maybe, it would take a lot, I don't know, a lot. But 20 years in the future, like 20 years in the past, computers were absolute crap compared to what they are now. 20 years in the future, this might be a small number. So let's give them a lot of power to make sure that we're a little bit future-proof in these things. So a quadrillion guesses per second, yeah, they're cracking that instantly. 32 bits of entropy, they got that covered. So let's crank up our password, and let's go right to the standard of uppercase, lowercase, number, special character, minimum length of 8, and assuming it's a purely random string, a string that you'll never use as your actual password if you're remembering it and not using a password manager. With a quadrillion guesses per second, yeah, they're cracking that in seconds, but that's a lot of power. But more telling is the bits of entropy. 51.9, that's well short of our 80, which is our general standard of this is actually secure in the world of security. So let's try to get to 80 and see how much time this is going to take, even at a quadrillion per second. So we get to 64 bits of entropy at 10. We're at 71, so we're close. Let's get 12. We should get to our 80. 77.9, we're almost at our 80 bits of entropy. 1 quadrillion guesses per second. All we did was change this from 8 to 12. We added 4 characters. It takes them 9 years to crack that password. If we crank this up to 15, they're never cracking that password. And if you have a password manager and you punch in 20 for your password manager and have it actually generate random passwords of length 20, the sun is going to burn out before they crack your password. Your password is secure at this point. We can confidently say they're not cracking that thing at 129 bits of entropy. And somebody said just add a 0 to it. Too bad. Even the computer can't crack it. Yeah, that number with 324 bits of entropy. We got gobs and gobs of entropy there. Oh, I didn't even get to do my favorite demo. We'll have to wait till next time. In my Spotify